All right. So we got the theory out of the way. I'm gonna send you this document afterwards. So let me just write down this is the theory. Now let's do some practice, man. Let's go down here, practice. So, dude, with these circuits, really the most important thing is finding the equivalent resistance, dude, because the rest is formulas. The rest is, and it's only two formulas. It's not like, well, it's really only one. I guess if you count the power one, then I guess that's two. But Ohm's law is really all you care about. So finding equivalent resistance is the most important part. So let's draw a circuit here, and we're gonna find the equivalent resistance before we do anything else. Here, and then at your voltage source. We don't really need a voltage source since we're just finding equivalent resistance, but we'll add it, just to build a habit, I guess. This is gonna be V, and we're going to find the equivalent resistance of this circuit, where R1 equals 3 ohms, R2 equals 4 ohms, and R3 equals 7 ohms. So you can try to solve it by yourself right now. This is the first one, so I'm gonna do all of them, but I recommend that you try to do it. You pause the video, try to do it yourself, and then see if you get the same result. And then if you get a different result, then correct me and tell me how stupid I am. Okay, so I'm gonna start. So first we have to, uh, what's the word? We have to see if it's in series or if it's in parallel. In this case, it's pretty clear it's in series because like I said, the easy way is just to see if the current can go any other direction, and it clearly cannot. Like the current is trapped; it can only go one way. So it's in series. Okay. Now to find the equivalent resistance in series, it's just the sum of all the resistors that are in series. In this case, they're all in series. So R1 plus R2 plus R3. That's your equivalent resistance. So now we substitute the values that we got up here. 3 ohms for R1 plus 4 ohms plus 7 ohms. This is equal to 14 ohms. And that's your equivalent resistance. Okay. Now, if we gave a value to the voltage, let's say that voltage equals, I don't know, 21 volts. Now I can ask you to find the current. So what do? We use Ohm's law. I always write down the original equation because, like, I don't know if I told you. I think I have. I don't memorize anything, dude. There's nothing to memorize. Just learn one thing, and then solve for what you need. So I just learned the basic Ohm's law, and now okay, I need current. Let me solve for current. It's voltage over resistance. Okay, let's see. 21 volts over 14 ohms. So now, listen, we're gonna leave this as an exact value. We're not gonna do decimals. 21 over 14. We're just gonna divide both by 7. Simplify. We got 3 over 2 amps. Okay. I mean, yeah. 3 over 2 amps. Fine, whatever. We'll do decimals. Okay. So now that we have the current, we can find the voltage drops in each resistance. So we can find V1, we can also find V2, and we can find V3. V1 is equal to I times R1. V2 is equal to I times R2, and V3 is equal to I times R3. Just a quick side note. what it means to have the current constant, it means that the current is the same here as it is here. You can measure current with tools. There's tools for that. And if you put the measuring thing, I forgot the name in English, but whatever. The measuring thing here, it'll give you the exact same as here because the current does not change. It doesn't. It's constant the entire way throughout the series circuit. Okay, so that's why there's only an I here. Otherwise, it'll be like I1 times R1, whatever, depending on the situation. So now, dude, we just plug in values, brother. We literally just plug in values. Um, You know what? This is why I like fractions better though, because even though like 1.5 is it's an easy fraction to work with. Easy decimal to work with. I just prefer the fractions, dude. It's better for me, man. Let's see, 3 ohms is our one. So this is 9 halves volts. Whoops, amps. R2 is 4 ohms. So this is gonna be 6 volts. And R3 is 7 ohms. So it's going to be 21 halves volts. And let's see if we did this right, man. We can check our answers actually. Because the sum of all voltage drops should equal the total voltage. So I'm not going to add this. I mean, I suppose they all have the same denominator, so I could. But I'm just going to put this in the calculator. Okay. V1 plus V2 plus V3 should equal the volts from the voltage source. So we got 9 halves 9 halves volts plus 6 volts plus 21 halves volts. Let's see what this equals. 21 halves equals, so this equals 21. And our voltage source was of 21 volts. So it is correct. So yes, you can check your answers. There's no, with these circuits, I mean, honestly, I think with all circuits, you can, or well, all that I've worked with, you can check your answers pretty easily. So yeah, man, there's really no excuse to get these wrong. Okay, always check your answers. Okay, let's move on to a different circuit. Yeah, over here. All right, the voltage source. All right, here. Actually, you know what? We'll do that one later. I do this way too low, man. What the hell? Oh no, it deletes everything. Okay, my bad. All right, so let's do one more. Yes, sir. All right, man. This time I'm not gonna identify each of the resistances. I'm just gonna give them their value off the rip. And the voltage source is going to be 30 volts. Okay, dude. Should I number these? I feel like I should. So we can reference them later if you have any questions. Number one and number two. Alright, man. I want you to find the equivalent resistance, and then I want you to find the current. I wonder, you should be able to find the current, and yeah, man, that's what I want. Just yeah, exactly, that's what I want. Find the equivalent resistance first, though. The currents might be a little more tricky. Okay. All right, so let's do this. So in this case, man, we identify if it's a series circuit or a parallel circuit. What color did I use here? I didn't use any color. Okay. Um. Uh, so that's pretty clear. You got your current here. You got your current here. Splits up here. Man, it splits up again, dude. Splits up. Well, this is the same thing. Yeah, it splits up a couple times here and here. So we got a parallel circuit. Okay. So to find the equivalent resistance, it's the reciprocal of the sum of reciprocals. In this case, we have three different resistances or resistors in parallel. So we got 1/1/3 ohms. And you can do this in the calculator. I don't know what calculator you have, but if it can do fractions, then this would just give you the answer. The calculator would just give you the answer straight off the rip. You don't even have to do anything. It's very nice. But I'm gonna do it by hand. Okay. So you got 1/. We do the common denominator, which in this case, oh my god, it's gonna be brutal. If let's see, I'm gonna do it separately. 4 + 3/12 ohms plus 1/5 ohms. There we go. I have to multiply. Damn, yeah, big number, man. I wonder if this is right, man. 35 plus 12 is 47. And the reciprocal of that is 60 ohms over 47. I'm gonna put this in the calculator, man, because I am very terrified that I got this wrong. 1/3 plus 1/4 plus 1/5. Okay, it is correct. So this is the equivalent resistance, man. Let me rewrite it down here. What is it? 60 over 47 ohms. Notice there's just a nice little math thing. Notice how the ohms are in the denominator here, right here. So when you do the reciprocal, when you get the common denominator right here, you do the reciprocal because of this one up here, and the ohms end up on top again. So you can clearly see there's no math rules being broken. Okay, the ohms will end up on top in the numerator. Okay, so there's the equivalent resistance. So why do we need the equivalent resistance, baby? Well, since there are so many currents, let's start identifying them. Matter of fact, I'm gonna move this lower so that we can draw the currents. Okay. Um, uh, the current that starts at the voltage source is the total current. So we're gonna call this IT. And if you notice, it's the same logic from up here where the currents add up. The current that's, I guess, parallel to that. Well, I guess they're all parallel, but directly under it is also the same current. It's also IT. Okay. We're gonna talk about this later. How this is a net. This was called a net. And we're gonna talk about it later. Well, I guess it. Well, we'll see. We'll see. Notice that the currents are the same. So now the currents start to split up. We've got, what color do I use? You can't really see the orange one, can you? I guess I'll use white. The currents split up here. Here you've got I1, I2, and the same thing applies, bro. Same thing applies right here. There's I1 as well. And then we've got I3 that goes there. And I3 goes all the way around to here. Okay. So I wonder there's another node here. There's I1 splitting. So there's a different I don't think this is I2. I mean we'll see. I don't think this is I2 though. It's gonna be like I4. Okay. So why do we need equivalent resistance? Because equivalent resistance will give us IT. Voltage equals IR. Another way to write this is total voltage, I guess, from the source is equal to total current times equivalent resistance. So now we solve for total current. Yeah, the voltage it's the voltage source over the equivalent resistance, which is 30 volts, right? Yeah, 30 volts over 60 over 47 ohms. And this is equal to 30 volts over 60 over 47 is equal to 47 amps. Amps. So that's the total current. So now we know that the sum of all of these, of I1, I2, I3, and I4, is 47 amps. Okay, because that's the total. Okay, so now how do we find the other currents? Um, uh, let's see if we can figure this out, man. Listen, there are other techniques that, in this case, I would use. Me personally, I would use these other techniques, but we haven't talked about them yet. So we're gonna try to solve this with just Ohm's law. Um, we're gonna find out if we're gonna be able to do it or not. Okay, I think so, to be honest with you. But let's do it. Okay, let's do this. So let's try to find this first combination, I1 and I2. We know that I1 and I2 add up to form IT because they came from IT. So that means, what else do we know? Let me hold up my fan. Okay, what else do we know? We know if we use Ohm's law again, let's see. We know the voltage is the same everywhere. Voltage is the same everywhere because it is in parallel. And let's see. So we can find I2 with this resistance. Yeah, we can find I2 with this resistance. So let's see. Voltage equals I2 times resistance of 3 ohms. All right, let's use that. We are going to check our answers, by the way. So fear not. So if voltage equals I2 times the resistance of 3 ohms, that means that I2 equals voltage over the resistance of 3 ohms. And the voltage is 30, and the resistance of 3 ohms is 3 ohms. The voltage is 30, right? Yeah. So that means that I2 equals 10 amps. Does that make sense? So far it does, because 47 halves is like 23.5. So that makes sense. It's less than the total. So far so good. So now we have I2. We can solve for I1 here. I1 equals IT minus I2. I1 equals, what is it, 23.5? Yeah, 23.5 amps minus 10 amps, which equals 13.5 amps. Okay, so we found I1 and I2. 10.5. Now the thing is that I1 splits up into I3 and I4. So that means that I1 equals I3 plus I4. Do you see this? Like it splits up into I3 and then I4. So I1 equals the sum of I3 plus I4. We're gonna use the exact same logic, man. We're gonna use the exact same logic. Um, uh, let's see. V equals I4 times the resistance of 4 ohms. Okay, okay, there we go. So that means that I4, let's write it next to it. I4 equals voltage over R 4 ohms, which equals 30 volts over 4 ohms, which equals 15 halves amps, 7.5 amps, which is less than 13.5. So far, so good. And now we find I3 with I1 minus I4, which is 13.5 minus 7.5 amps. That's, what is that? 13.5 minus 7.5. Whoops, hold up. 13.5 minus 6 amps. Alright, so now we've got I1, I2, I3, 6, and I4, which is 7.5. Seems correct to me, but I'm not gonna lie to you. Honestly, since we got our answers from other processes, like this process that we did, the IT equals I1 plus I2, we've kind of already like foolproofed it, like with the check and everything. So I'm going to do another check. I'm just gonna check this for my sake, or and also for yours, of course. But just to check that it's correct, I'll explain what I'm doing later. Okay, this is one of Kirchhoff's law, by the way. Let's see how did it go? It was like, all right, I'm gonna do it this way. Yeah. So we've got there's only one. Damn, that's crazy. But I'm kind of hmm, I'm going that way thing. Maybe minus. I3 is 6. Oh my god, dude, we got it. We got it, baby. This is supposed to equal 0. 30 volts minus 5 times 6. 5 ohms, by the way. Yeah, that is correct. Okay, dude, so we got it. We got it. I'll explain this later, but just trust that I've checked it and that it's correct. Okay. Um, uh, so yeah, so these are your answers, man, right here. Let's box them up right here. And there you go. Let's do, I mean, honestly, that example is pretty good, but I do want to do one more where I want you to see that you can have a series circuit and a parallel circuit in the same circuit. Okay. And in this one, we're just gonna find the equivalent resistance because this was a pretty good example where you can find the different currents. Okay. Wait, why did I do this in white? I'm doing it in yellow. Okay. So we're gonna do, I don't know. We're gonna do small numbers here. 2 ohms, 3 ohms, 1 ohm, and 2 ohms. No, 4 ohms. Oh, they both add up to five. Okay, that's crazy. Anyways, well, let's do 10 volts here then. Okay, dude. So now we've got a couple resistances in series and a couple in parallel, right? Because there's a current. The current goes through here, and then it reaches this point, and then it goes here and here. So this is in parallel. However, this current here goes through two resistances in a row without it being in parallel. But right? So we do have some pieces that are in series. What do we do here, bro? We start simplifying. We do what's called simplifying the circuit. Okay. So we identify that these two are in series. So we do what's called R prime. It is basically the equivalent resistance of a piece of the circuit. R prime equals 4 ohms plus 1 ohm. So R prime equals 5 ohms. And this is unnecessary, but I'm gonna do it so you can visualize it. We're gonna redraw the circuit. Okay. So we got 2 ohms, 3 ohms, and now, dude, we got R prime, 5 ohms. So you see how these two combine, and now you've simplified the circuit. So what you've got now, you forget about the old one, and you focus on this new one. What do you have now? Now you have two resistances in parallel. So you do R double prime. R double prime is going to be that second equivalent resistance. It's going to be 1 over 3 ohms plus 1 over 5 ohms. Okay, do you see this? By the way, you know what? I don't want you to build this habit, dude. Put it in the calculator, okay? Like, forget about doing the math by hand. So it's gonna be 1 over 3, 1 over 1 over 3 plus 1 over 5. And 15/8 ohm. That's gonna be R double prime. So now, dude, we're gonna redraw it one more time and check what we got. Shit. Here. Okay, I don't know why I extended it so much, but whatever. Got 2 ohms, and now we've got R double prime here. 15/8 ohm. Bam. There you go. Dude, and what have we got here, bro? This is just a series circuit, man. This is the same as the first one. No, it's even easier than the first one that we did. Check it out. Now we do what? Listen, the reason you do the primes is so you don't confuse your actual equivalent resistance. Since this is gonna be the last prime, we call it equivalent resistance. You know, forget about the primes. We just call it equivalent resistance. And we do 2 ohms plus 15/8 ohm. And then I'm gonna put that in the calculator. 2 plus 15, whoops, 15/8 is 31/8.